Perfect. Thank you, Professor Dugat, for the nice presentation. Let me see how we should do. Should I share my screen or?
Yes, you could share your screen, please.
Let me try to see whether I do it, because in fact I have a. Alors, autoriser. Désactiver. OK. Sélectionner. OK. Autoriser. OK. Does it work? Alors, hein? Non?
Not yet.
Désactiver, sélectionner une fenêtre sur un écran.
Have you uploaded already?
Okay. Now I see what I do. Okay. Is it? Apparently, it doesn't work.
No, you have the.
You have to.
Okay, so it's done. Okay, and then.
So could you share your screen? I mean, if you just press on that and select the screen.
Excuse me. In fact, I'm trying to do it. Yeah.
Okay. You see the green button.
Yeah. In fact, you see what happened to me. I already told you about the story. In fact, I broke my PC 3 days ago, and I'm using the Mac of my wife, which I'm not familiar with. I'm really.
Okay, I understand. So we all go to that situation. Have you
in the worst case, maybe. Okay.
Yes,
Because,
so
we will share the screen. Is it okay?
Yeah. Maybe this is the best way to do it properly. Yeah. Let me try last time. Yeah.
Sure.
Okay, so I'll download your talk and I'll share the screen in case. That's the second option.
So this didn't work, yeah? So this because I'm trying, in fact, to do it, but I see that somehow it doesn't work. Okay.
Yeah, I'm also not technically savvy, so I face a
So
problem.
please go ahead.
Okay, I'll share the screen. Just
Yeah.
give me half a minute.
Oh, okay.
Yes, is that okay?
That's perfect. That's perfect. So I'll tell you when.
Yes.
Okay.
Yeah. So you may please start.
Okay. So as I said, I broke my computer, and I didn't have unlike Jenny List, who had the same problem also. I didn't have a recent backup, so in fact I tried to adapt a more general talk. So this is why I changed the title, and maybe also the content will change. But after all, I think it's not maybe a bad idea, because I was supposed to discuss with you the status of this 10 years precise measurement of the Higgs properties. And I think this has been discussed at length in the various presentations that we had this week. So I will have pretty little to add to that, yeah? So rather, I think it would be good to summarize again all the arguments for pursuing the precise measurement of the Higgs and the search for additional Higgs states or additional new states beyond the one that has been discovered, and try to give some justification for all what will come in the next few years or decade, yeah? And I'll try to do that in the simplest possible way, although this has also been discussed in some of the talks that we had this week. There was this theory talk by Tuhim Roy, and also some search related talks by Aaron Nayak and Isobel Ohalvo. And I'll try to be a little bit more comprehensive and simpler, and also kind of try to cover some complementary issues, okay? So I'll first discuss what is the status of the standard and the model, the Higgs. then try to list all the shortcomings of the standard model that really call for Higgs beyond, for new physics beyond the standard model, and then discuss the main 3 avenues for beyond the standard model that everybody is talking about, and try to make some conclusions for the future. So we can go to the next slide.
Yeah.
Okay. So let's a little bit recapitulate what happened. I mean, where we are just before the discovery of the Higgs, say in the year 2011. Okay. So we had the standard model, which is our theory for the electroweak and stronger interactions, and it was based on 3 pillars. The first one, of course, is that it's a quantum field theory, so it includes special relativity and quantum mechanics as a base, and then it is based on invariance with respect to a gauge symmetry. So the symmetry was S23 for the strong interaction and S22 cross U1 for the unified description of the electroweak, the weak and electromagnetic interactions. And then there was the third pillar, which is the electroweak symmetry breaking mechanism for mass generation. So the idea was that you have to introduce, in addition to this gauge symmetry, and which basically describes the interaction of fermions through the exchange of gauge bosons, you had to include an additional doublet of scalar fields, which was a kind of novelty in what we used to have at that time. You introduced this scalar fields with a potential that makes that the potential itself doesn't obey the symmetry of the theory. So this leads to what we call spontaneous electroweak symmetry breaking. This is because this Higgs field develops a vacuum expectation value, and 3 degrees of freedom go to make the W plus W minus and Z boson mass, and there is 1 degree of freedom left, which corresponds to physical particle, physical scalar particle, which is the Higgs mass, the Higgs boson, the Higgs field. Okay. Now this theory is pretty nice mathematically. It's really consistent. It allows you to have, it's a normalizable theory. It's unitary. It's perturbative, at least at high enough energy. It might be problematic for a certain value of the Higgs mass, because then you lose perturbativity and also probably unitarity, but we'll see that it's not the case with the Higgs that we have observed. And all these properties allow you to make extremely precise prediction. And we had prediction now at the level, at that time already at the level of next to leading order, and even a little bit beyond for some aspects. Not the Higgs one, but for some other aspects we had really calculation at the next next to leading order. Okay. And in the year 2010 or 2000, the lab was already over a decade ago. Tevatron was finishing its campaign for collecting data at PP collisions at 2TV, and we had extremely high, highly measured observables, like the psi squared theta W, the W mass, the top quark was discovered, and also its mass was discovered, measured precisely. So we had extremely highly accurate tests of the standard model. Okay, so the precision of the predictions, which is of the order of say 1 per mil, was chiefly matched by the experimental accuracy, which is at the level of 10 to the minus 4. Okay, for some observables. So. And it happened that everything fitted very well, except for small details. We had still a little bit of problems for the 4 backward symmetry and the left-right asymmetry, but not more than 2, even 3 sigma. And the theory was really satisfactory. Okay, we also had the same problem, in fact, with the G-2. At that time, it was 2.3 sigma. Now it's a little bit more. But this you cannot say exactly that it's really a discrepancy compared to the standard model prediction, because many people believe that the prediction is not accurate enough in the case of the G-2. Okay, so I'm not getting to this issue, but okay. On the first sight, one can say that the theory matches experiment in a kind of perfect way. So the year 2011 and even 2011, because I'm not saying 2012, because already we had an indication that the Higgs was there at the end of 2011. In 2011, so there was only one aspect of the theory that has not been tested. It was the scalar sector, the scalar sector, and the LHC was really devised to test the scalar sector. So it was devised to verify the Higgs mechanism. I really find that this mechanism really generates the masses of the particles, and in particular relates the coupling of the Higgs particle to the fermions and the gauge bosons to their masses. So really the couplings are proportional to the mass. Of course, discovered the famous particle that is behind all that. And if in case of non-discovery, you have to find the ingredient that does the job, because the LHC energy was in fact sufficient to make that any phenomenon at the TV scale and should be in principle observable at the LHC. And if the Higgs was not there, something should replace the Higgs, and its scale, the scale at which the new phenomena associated to this new mechanism that replaces the Higgs should be below the TV scale. So in some sense, this LHC was a kind of no losing factory, where either you discover the Higgs or you find something that really plays its role and replaces it. Okay, and next slide. This is what happened 10 years ago in July 2012. So really, we have observed this particle, and for us, it was a spectacular success. Okay. Now we are 10 years. Let's stick to this slide, because I don't have, I couldn't have the chance to say a few things about what happened since then until now. So since that's 10 years, so let me give you just a flavor of what happened, but just in words. And I wanted to use one of the slides of Maria Cepeda this morning, which really summarizes what has been achieved so far. And she had a very nice summary in the third slide of her talk. So I'll just go through it, but unfortunately I cannot show it to you. So the mass was measured to be 125 GeV, and this at the permeable level. So it's a very precise measurement. And it happens that with this mass, the standard model can be extrapolated all the way up to the Planck scale. You heard probably in the talk of Rohini Goldball that there is a problem with unitarity. If the Higgs was too heavy, something like 1 TeV, you had a problem with perturbative unitarity. The cross-section grows beyond any bound. So basically, you are spoiling the conservation of probability. But this doesn't happen for a Higgs mass of 125 GeV. What could happen for a Higgs mass of 125 GeV is that the scalar potential that breaks the symmetry might be unstable. The idea is that the Mexican hat potential needs a quartic coupling, a self-coupling, a Higgs self-coupling, and the Higgs self-coupling is proportional to the Higgs mass squared. It needs a Higgs coupling that is such that it should be positive. It should be positive. Otherwise, the potential is slightly is reversed, and the minimum it's at minus infinity rather at the vacuum expectancy value of V of 250 GeV that we need. Okay, so we need a positive coupling, and it happens that this coupling is subject to radiative corrections, and in particular to corrections due to the top quark, which has the strongest coupling to the Higgs. And if the coupling is small at low energies, it can become negative at say the Planck scale. So for the coupling to remain positive, you need a Higgs mass that is something, and that is something of the order of 125 GeV or so. Okay. Now this stability of the potential depends also on the mass of the top quark. And for the value that has been measured recently by CMS, 171 something, 0.5 or so, it happens that in fact the Higgs, when you extrapolate the Higgs coupling, it stays positive up up, non-zero and positive, up to the Planck scale. So the mass of 125 GeV is really a good number for extrapolating the standard model up without the need, and this is the main issue, without the need of geophysics up to some 10 to the 18 GeV or so. Okay, so this is an important information. We have seen also that the width of the Higgs has been measured with a precision of, say, 50% or even, I think it's factor of 2 or so. And this is also kind of interesting. That means that there are no new states that in which the Higgs decay into, and in particular, the invisible decay has been measured with at the level of 20% or so, and 20% is precise enough to be kind of confident that there are no new states strongly coupling to the Higgs in which the Higgs decay into. So there is no, for instance, dark matter particles with large coupling to the with masses below 125 divided by 2, 165 GeV, and coupling strongly to the Higgs. So it's already a good information. And we have checked that the Higgs is a spin zero particle, although we did it in a kind of very, very, very rough way, because we did it through the Higgs decays into WW and ZZ, mostly in ZZ, while we knew from the start that if the Higgs couples to ZZ, then it should be CP even. But in any case, I'll come back to that. So we also measured the various couplings of the Higgs to gauge bosons and fermions, and we have realized that the couplings to gauge bosons are standard model like up to some 15% accuracy. The Higgs couplings to fermions are also standard model like up to, say, 25% precision. And the only thing I heard about this, and which was in fact surprising to me because I didn't know, so maybe I didn't follow closely all the the new developments that happened in the last few weeks, but I see she quoted a TTH cross-section, which is in fact 3 sigma away from the standard model expectation. So maybe there's no physics in there, and I'll think about this problem a little bit more closely because I'm really interested into this result. Okay, so in summary, we have 10 years after the Higgs discovery, we have a really plethora of results which indicate that we really had a Higgs that is standard model like. Okay, that's really a good information. Now we go to the next slide, if you allow me. So we have now a Higgs, and it's almost standard model like. So the standard model is confirmed in a spectacular way as the theory of the Electroweak and the strong interactions. And the question that everybody asks, and all the time I give, no, this is the question that comes into the mind of everybody, is particle physics closed, and should we stop physics and, I don't know, go for vacations or go to... And the idea, of course, the answer is not. And this is what I will try to do in the next half an hour. First of all, let me tell you that all the precision by which we have measured all these properties of the Higgs is not, in fact, enough, because if new physics is of electroweak origin, like it is the case for many extensions of the standard model, I just quote the case of supersymmetry, for instance, the deviation of the expected modification of the Higgs couplings or the Higgs properties that are generated by supersymmetric theories are in fact expected to be small. It's a weak theory, so it should be of the level of the radiative corrections. Radiative corrections are order alpha over pi, and therefore are at the level of a few percent. And we are not there. And for the moment, we are at the level of 15%. 30% or 25%, and therefore we have still a long room, large room for deviations of the couplings from the standard model expectation. And this is in fact what will be done at the high luminosity LHC, because there clearly you can, for instance, go and measure the couplings with a precision of 2 to 4%, which is already at the level of what you expect from the radiative corrections, although not yet, because radiative corrections can be also at the level of 1%. You can the high luminosity LHC, you can, and there are also other aspects that have not been discussed so far in the context of the LHC, which is, for instance, as it has discussed several times, the Higgs self-coupling, which is only measured at the level of 50%, the coupling to second generation, because we know the Higgs, of course, is responsible for the mass of the third generation fermions, but what about the second generation? So we need high luminosity LHC to measure the Higgs into mu coupling with an accuracy of, say, something of the order of a few percent. And we also have a problem with the CP nature of the Higgs, because, as I said before, you cannot really do the CP measurement, I mean, of the Higgs into in the Higgs into ZZ channel, because what you need to do is not to check that the Higgs is a CP is a spin zero, is a CP even object, because it couples to ZZ, so it should be a CP even object. But you need to check whether it has an additional component from CP odd. And it could be this, and this component could be small. It could be small as a few percent or so. And it appears that indeed, in order to check that, you really have to go and check it in channels in which the Higgs couple to fermions. Okay, so the best way would be to do it, for instance, in glue into Higgs, which appears to the top Karl group, with the Higgs decaying into tau tau, because you know that the scalar and the scalar and pseudoscalar couple kind of democratically to fermions, which is not the case of gauge bosons. Pseudoscalar doesn't couple to W and Z's. Okay, so apparently this can be done at the high luminosity LHC with the level of a few percent to measuring the angle, the admixture of CP odd in addition to the CP even component of the standard model Higgs. And well, if I understood properly, you can also measure the Higgs self-coupling, which is not for the moment discussed at all. So we will have really the chance of really probing in more depth all these properties. And in fact, for some of them, even the HL-LHC, the high luminosity LHC, is not sufficient. For instance, you need, if you really want to measure the Higgs self-coupling in a better way, you have to go to higher energies. And even these couplings to gauge boson fermions can be measured with a much better accuracy, as we just heard in FCCEE and ILC. Okay, then you increase the accuracy by another factor of 10. Okay, so. And then if you do so, then you really get at the level of the radiative corrections, and therefore you are in a much better shape, and you are in much better position to claim that this Higgs really standard model, and there is no impact of new physics whatsoever in its properties. Okay. Now we know that in principle, we should observe a deviation, because we know that the standard model is not the theory that is really the most satisfactory in order to describe the physics that we know about. And we have the arguments that there is something beyond the standard model, and we have three arguments for that. Okay, so, and we believe that by measuring the Higgs in a kind of more accurate way, and also because I didn't cover this aspect, but it's clear that it's not only the measurement that count, but also the search for the associated states that are predicted by this new phenomena that are beyond the standard model. These particles should be accessed at some point, and if they are the weak scale of at the TV scale, one should discover them. And if it's not at the it's not the case for the moment, it will possibly be the case at the high luminosity LHC or at high energies, or at the FCCHH, for instance. So we have plenty of room for for discovering other states. Okay, so now let me now come to the arguments that push us, in fact, to go to further precision and further mass reach in the direct searches. And there are three, in fact, of such arguments for justifying our expectation that there should be something in addition to the standard model that we have presently. So the first type of argument is of aesthetic nature. Okay, the model is too complex, has too many ingredients. We need the theory that has only a few basic parameters and a few basic principles and ingredients. So that's okay. One possibility. A second one, which is more important and of course more direct, is the fact that there are few experimental facts that are not really explained in the context of the standard model. Okay, the standard model doesn't explain all the phenomena that we observe in nature, and I will go through that. And of course, there is the hierarchy problem, which has been discussed already in one of the presentations, the one of Tuhim Roy, for instance. There is the hierarchy problem, which tell us that there should be something that that forces the Higgs to be light and to have a mass of 125 GeV. Okay, so let me, in a very briefly, but in kind of general way, try to summarize all these arguments. Okay, so let's please go to the next slide. So let me briefly describe for you the what I call the aesthetic argument. Okay, because aesthetics, in fact, was behind the construction of the standard model. We went to construct the standard model. We constructed the standard model for arguments of symmetry, arguments of simplicity, and arguments of minimality and economy. Okay, and also arguments of aesthetics, because also even symmetry is aesthetics because it's related to a geometrical principle, and therefore you can relate geometry, if you wish, to beauty somehow. Okay, now the standard model is not really aesthetic. It's something that is extremely complicated, because you need 19 parameters to describe everything. You have all the fermion masses, all the mixings. You have it's particularly true in the context of the fermionic sector. It's and all the parameters are put by hand. I mean, the standard model doesn't predict the fermion masses. It relates the masses to the couplings, but it doesn't say anything on the masses itself and on the mixing. Okay, so it's really annoying, and in particular that all these masses are really completely different from each other. When you see the mass of the electron and the mass of the top quark, this gap is extremely huge, and it's a little bit complicated to digest, if you wish. Okay, now the other aspect, of course, is that the symmetry breaking, the fact that the mass term in the scalar potential that makes that the symmetry is broken is negative. You have a mu squared there that is negative, and this is really put by hand, and it's really hard to justify why this parameter is negative. Okay, so it's really just an ad hoc assumption, and you put a mask that's square that is negative in your Lagrangian. And okay, this many people find it a kind of non-natural. Okay. Now the other argument, of course, is that you want full unification, which means that at the end of the day, you need also to include gravity in the game. Okay. Gravity is, of course, has a different status because it couples too weakly to the rest of the model, and therefore it is not testable at the collider side. So you really have to go to observational physics, astrophysics, in order to test this. But we already know theoretically that we have a problem because we don't have a quantum theory for gravity, and the situation with the spin 2, because contrary to the other attractions which are mediated by spin 1 particles, here the graviton is of spin 2. You don't even have a QFT for it. So it's a little bit of a complicated situation for that. So, but still, at least the fact that it doesn't include gravity means that there is something in beyond anyways. Okay. And then another argument is unification. In fact, we are talking about a unified description of the strong and electroweak interaction, but in fact, this unification actually doesn't take place. Because for unification, you need that at some point, you need to embed the standard model into one single gauge group with one single coupling constant. And this doesn't happen because if you evolve the 3 gauge couplings, the one of SU3, the one of U1, and the one of SU2 with energy, including only the standard model particle content, you realize that this coupling do not converge at some point, and therefore there's no unification at a high scale. Okay, so the 3 couplings do not converge. So there is, even if you believe, so even if you So that means that the paradigm which put forward the standard model, which is the need of unification, doesn't work in practice. You need some additional degrees of freedom in order to make it work. Okay, let's go to the next slide, please. So these are what I call the aesthetic arguments. Okay, there are others, but I will not go, of course, into all of them, but I'll try to list all only the main ones. And after all, these are only aesthetic, as I said, and therefore, they are not really strong, because after all, the nature has not to be beautiful or economic. If we have a model that technically works, phenomenologically works, after all, we should be satisfied with it, even if it's complicated, even if it's ugly, even if it's not economic. Okay, so this argument is maybe too subjective, so it should not be put on top of your list of objections for the standard model. Okay, you can complain, but you cannot rule out the standard model just because of this argument. Okay, there are instead very much stronger arguments against the standard model, because if you have a model, it should explain everything. In particular, it should explain all the phenomena that you observe in nature, and we should know for sure that there are phenomena that are present in nature that are not explained by our model. And there are at least three aspects that are not explained in the standard model. The first one is the neutrinos. The neutrinos, in the standard model, the neutrino is left-handed only, and it's massless. Okay, and we know that neutrino oscillates. That means that they have masses, and their mass is not coming from the Higgs. So that must be. So we need some additional phenomena in order to generate the small neutrino masses. Okay, for instance, we can have a right-handed neutrino, which is completely different from the left-handed neutrino, contrary to the other fermions of the standard model, in which the right-handed and the left-handed guys are in different representation of SU2 cross U1, but they have the same mass, they are the same particles. Here, it should be the same. The right-handed neutrino should be more massive, if you wish, compared to the left-handed neutrino, and therefore, this particle could even be a Majorana particle, which is then completely different from the Dirac particles that are contained in the standard model. So, in order to explain the neutrino masses, you most probably need physics beyond the standard model. Okay, and in fact, one option, but I'll come to this point later. But anyways, let me now go to the next issue, which is also not explained by the standard model. This is the baryon asymmetry in the universe. The fact that we are all the universe is made of particles and not by antiparticles, and the ratio is 10 to the 9, which is huge. Okay, while you expect that according to our early cosmology, we had only energy, and therefore this energy will split into an equal number of particles and antiparticles. So at early times, we should have really the same. So we need to explain why this happens. And one of the explanations was given by Sakharov. This is the fact that you have a kind of if you wish, some biogenesis, or which is kind of consequence, among other things, because they have three conditions for that, but among other things, the fact that CP symmetry is violated. So if you violate CP symmetry, you also violate baryon number, and you have some phase transitions that are involved. Then you can explain what the baryon symmetry in the universe. Okay. Now, the point is that the CP violation that you have in the standard model is absolutely not sufficient to have this baryon symmetry. Okay, so you need an additional source of CP violation, and this is an important aspect. This is in fact why it's very important, in fact, to test the CP nature of the Higgs. Maybe this additional CP source of CP violation is hidden in the Higgs coupling. So this is why you have to do the job. But anyways, you need an additional source of CP violation in order to violate to explain the baryon symmetry in the universe. Okay. Now a third argument is the argument of dark matter. So we know that the visible matter of the universe is only 4%, and there's 25% of the matter in the universe is invisible. And apparently, from astrophysical arguments, this particle should be massive. This is the cold matter, the cold dark matter paradigm, the WIMP paradigm, weakly interacting massive particle paradigm. And in such a part, it's in the standard model, there is not such a particle. You know, a particle that is weakly interacting, massive, neutral, electrically neutral. There is a neutrino, of course, but the neutrino is not massive. So we need a new particle, an additional particle, in order to explain the dark matter in the universe. Of course, there are other solutions now. People are thinking about black hole. They are thinking about other non-matter explanation of the dark matter, non-particle physics explanation of dark matter. But still, the best apparently candidate is what we call a WIMP, neutral, weakly interacting, massive, and stable particle. Okay, so at least for these three issues, we need something that goes beyond the standard model. Now, there are, in fact, models in which you can have all these three ingredients implemented and have a kind of an extension of the standard model that can cope with all this desiderata, okay, these arguments. And one of the options would be, for instance, a ground unification theory like SO10, which then allows you to have, to be still in the unification paradigm. And SO10 happens to have a representation, a fundamental representation of dimension 16, in which, in addition to the 15 chiral fermions of the standard model, you have space to include one neutrino, one right-handed neutrino, one Majorana neutrino. Okay, and this you have to do for the 3 generation. Okay, so you have to include, and you can manage, in fact, in such a way that where first this right-handed neutrino has the properties, the couplings and the hierarchy, if you wish, in masses and mixings that explain basically what happens in the neutrino sector of the standard model. In fact, you can explain the neutrino masses and mixing of the standard model just using this SO10 neutrinos with large masses. Okay. On top of that, you can manage, in fact, in such a way that this right-hand neutrinos have some CP violating couplings to leptons, and therefore they lead to some decays into different decays into antiparticles and particles, and this would explain the baryon symmetry in the universe. In fact, you can have what we call biogenesis, the fact that the baryon symmetry on the universe, there is a baryon symmetry in the universe by triggering, by generating a lepton asymmetry. Okay, so you generate biogenesis through what we call leptogenesis. Okay, and this you can do, in fact, easily in the context of this SO10. Okay, now for dark matter, we know for a long time, in fact, that the best dark matter candidate, although it's not a massive particle, is the action. Okay, so in fact, an action can be easily, in fact, included in this SO10 description of the physics. So we have a model, and on top of that, and this is also one of the best arguments, on top of that, you know that you can have gauge unification, gauge coupling unification in SO10, because if you break SO10 in with an intermediate scale, with a scale, say, you go breaking SO10 into SU5, and then times U1, and then SU5 into SU3 cross SU time SU2 cross U1, or you do it through an SU4 Patti-Salam model, you have a possibility of having gauge unification because you have an intermediate step, and at this intermediate step, you can shift or arrange the couplings of the gauge couplings in order to that they match at the unification scale. In fact, you can have unification in the context of SO10 just with the neutrino, the standard model particle content, and in additionally with the right-hand neutrinos. So you can have, in fact, a model that explains all these aspects, and in particular includes unification and also dampen, comment dire, weakens a little bit the arguments of, complexity of the model, etc., because you know that all the fermions now are in a singular representation of SO10, etc. So you can in fact manage to have a description that is really unified and explanatory for all the phenomena. The only problem is that in order to do that, what happens is, sorry, I don't know what happens, but in order to do that, you need an intermediate scale at which you do this intermediate breaking, and at which you generate, inject the heavy neutrino masses. You need it to be at very high. In fact, you need it to be at the scale of 10 to the 8, 10 to the 9 to 10 to the 11 GeV. And in between now and then, there is basically a desert. And this is a little bit annoying in the sense that, of course, we have indeed an explanation or a theory that explains all the aspects of the shortcomings of the standard model, but this theory has to appear only at the scale of 10 to the 10 GeV, which is basically untestable at our level. The only thing which is maybe the only option and the only hope is, of course, the dark matter part, the dark matter issue, okay? Because we need the action should be light, and therefore you just need to make a very, very, very precise and sophisticated experiment in order to observe particles that are very light and have a very feeble couplings to the standard model particles, okay? So it might be indeed that we have indeed a way of unifying everything and explaining all the what is not explained in the standard model, but at the cost of being basically non-predictive. You cannot predict anything, or at least at the scales that you can probe. Okay, so you cannot verify such theories. Okay, so we would be a bit stuck in this context. And fortunately, we have other arguments in favor of new physics that force us, in fact, that imply automatically the presence of new particles at the scales that we can probe. And this is what we are discussing in the next slide, to which we can go, please.
So Abdullah, we have another 15 minutes. Yeah.
15 minutes, just
Yeah.
perfect. Okay. Oh, but in fact, I didn't realize because I'm not looking at the watch, but please stop me whenever you, okay. Now, there is the hierarchy problem that I can go very quickly through because it has been discussed.
And take a bit more time. It's fine. You are the last of the session.
Pardon?
You can take a bit more time. You are the last of the session.
Yeah, but I was supposed not to. No, let me. I think I will go very quickly because. Thanks for the proposition, anyways. So we know that for consistency of the standard model, we need a Higgs mass of. We need a Higgs mass of 125 GeV. Okay. In particular, that just for consistency, not having unitarity, etc. Because if Higgs is heavier than 1 TeV, we have a unitarity. And of course, to give masses to W's and Z's, which have masses of the order of 100 GeV, you better have an object which has a mass of 100 GeV. But you know that if you start to include the radiative corrections to the Higgs mass, you find corrections that are not logarithmic, as in the case of the fermion, not vanishing, as in the case of gauge bosons. They are quadratically dependent on the scale at which you extrapolate your theory, up to which you extrapolate your theory. Okay, and this lambda squared, this quadratic, we call them divergences, because we want to extrapolate the standard model up to the highest possible scale, and the highest possible scale is the Planck scale, 10 to 18 GeV. So the Higgs mass, if you really want to extrapolate the standard model up to ultimate, up to the ultimate energies, you, rather than getting masses of the order of 100 GeV, you get masses of the order of 16 GeV, 118 GeV. Well, you have an alpha over pi, 118 GeV. Okay, so that means that the Higgs mass has a tendency to be close to the Planck scale and not to the weak scale. And the only way, in fact, to make, within this picture that the Higgs mass stays small is to include the higher order corrections and to arrange in such a way that all the higher order corrections cancel make that this lambda squared divergences of contributions disappear, and at the end of the day you are left only with the very small contribution. And this is of course unacceptable for many people. This is unnatural for many people, because that means that basically you are canceling the 10 to the 18 GeV contribution, various 10 to the 18 with the fine-tuning of the order of 10 to the 16, which is for many reasons unacceptable. Okay. Now that means that we have a problem with the Higgs boson. Now, of course, maybe we are missing something. Maybe we are missing a very important ingredient, and well, there is a natural way to explain it, but we don't know about it. So we have to invoke, when we had to invoke a technical way in order to make that all these quadratic divergences are not absent. They are absent, of course, as I said, in the case of the fermions, because you have a chiral symmetry, if you wish, that that makes that the fermion masses are protected against large corrections, because the corrections are only logarithmic, and the logarithm of electron, if you wish, to divided by m Planck is still very small. Is in fact the correction of this type is only 20% of the electron mass, so it's something that is manageable. Gauge symmetry allows you to make that the photon stays massless, and also the gauge bosons have only small corrections when extrapolating to any big scale. And here in the case of the Higgs, we don't have symmetry arguments. Okay, some people, as I said, ignore it because about the theory, we know that the standard model is renormalizable, and the idea is that renormalizable means that you can in fact add a contrary term to the Higgs mass into the Lagrangian, which makes that this divergence is cancelled out. But we are getting into the philosophical problem, but it's a very important problem of giving a physical meaning to this contrary term, and this is why the problem remains. The fact that you have a contribution of this quadratic in the cutoff is a problem. So we have three. We have a problem, and we have now three avenues. We can go to the next slide. We have three options, in fact, in order to fix the problem. The first one is that we decide, because as we said, for fermions and gauge bosons, the problem does not cure. So we can just decide that, in fact, the problem appears because the Higgs is a fundamental spin zero particle, and one possibility to evade the problem is to make that the Higgs is not a fundamental particle. So it should be a kind of composite particle. And in particular, if it's composed of a pair of fermion and defermion, then you can basically avoid the problem. Okay, and this is one of the first options that have been proposed. And in fact, the first option was that the Higgs is a TT bar condensate. So it's a bound state of two fermions, and you can just combine the spins in order to make a spin zero particles. This is basically not like this, the pi meson, but like the Higgs is a sigma meson. Okay, the Higgs is a sigma meson, and this you can do just with either with TT bar, but you can even do it in fact with additional fermions that you invoke, an additional layer of fundamental particles that you put in the game, and this is the option with Technicolor. So you decide that there are technifermions that appear in the game, which make not only the Higgs is a condensate of two technifermions, but you can also in fact manage in such a way that all the gauge bosons also are the same. Okay, so these are really it's a QCD-like theory, but instead of being at 100 MeV scale, it is at the TV scale, at the TV scale. Okay, so some new layer of fundamental of compositeness should be observed at the TV scale. Okay, the only problem with this picture is that, of course, you are dealing with strong interactions, and strong interactions make a big impact. And we should have observed that first in the precision measurements of the electroweak observables that have been made before the Higgs and even after. They should contribute in a kind of large extent to the psi squared theta W and W, etc., etc. And of course to the Higgs, because if really the Higgs is a bond state, is a TT bar condensate or a Techni fermion condensate, then you should really observe something. And we have, for the moment, didn't see anything of this sort. So the scale is not now considered to be 1 TeV, but something like a few TeV. And therefore, you are becoming less natural because you are not solving a 100 GeV problem, scale problem by 1 TeV, which is reasonable, but with a little bit more, with a scale that is much higher. So this theories start to become unnatural in the sense that you need a much higher scale in order to explain what's happening at the Electroweak Symmetry Breaking scale. Second, next slide. So the idea is another idea is you remember that we need to extrapolate the standard model up to the gravity scale, the gravity scale, the Planck scale, which is the gravity scale. So if this scale was a few TeV, then we wouldn't have a problem because alpha, the correction would have been to the Higgs mass would have been squared, would have been alpha over pi, 10 to 1 TeV squared. But that would be of the order of 100 GeV, so it would be fine. And one idea would be indeed to make that the gravity scale is lowered to something like 1 TeV. And this is exactly the job that does for you the concept of extra dimensions. If you decide, for instance, that you have a fifth dimension where at least the spin 2 gravitons propagate, you can make that the effective gravity scale, the effective scale is not 10 to the 8 GeV, but something of the order of 1 TeV, okay? First of all, you lower the scale and therefore you basically make that when you extrapolate the standard model, you still have a Higgs mass that is correct. But on top of that, you do something that is the dream of everybody, is that you put gravity back to the game. And this is just the dream situation, because you have the possibility of including gravity in the unification paradigm. Okay. Now, of course, if you go into the details, there are several ways to realize the scenario. You have large warp, the universal extra dimension, etc., etc., and you have the way to introduce basically an infinite number of particles. This is the famous Kaluza-Klein towers of new of partners to the standard model particles, and therefore it has a huge impact on particle physics. Okay, and in fact, not only a huge impact on particle physics, so it's really a new domain of physics that you are trying to introduce, but also even the Higgs sector can be changed, because in fact, in the beginning of these models, you have a scenario in which you didn't need a Higgs in order to break the Electroweak symmetry. You can just do it by making that the boundary conditions are in some of this brains, etc., are specific. Okay, so you have the possibility of a Higgsless world. Of course, these are models are completely ruled out now because we observed the Higgs and it looked like it's a standard model but there are options for the Higgs sectors that are still possible with these models. Now, again, the only problem is that because the impact is so big on the Higgs couplings in particular and the Higgs interactions, that the measurements that we have up to now, the 10%, 15% measurements that you have right now, make that the scale at which this gravity should enter the game is not anymore 1 TeV, but it's now pushed to 10 TeV and even to 30 TeV. That means, once again, that this beautiful idea of lowering the scale to 1 TeV to explain everything has become a kind of unnatural, because the scale is not 1 TeV, but 10, 30 TeV. Okay, so again, we are in a situation where, because of strongly interacting theory, we have, because it's strong interaction theory, in fact, then you have a kind of unnaturality which is brought in the game because of the higher scale. Okay, now please, next slide, and this will be the third solution that I will just briefly go through, because it has been discussed in many talks. The third solution would be supersymmetry, because, as I said, In the case of fermion, you had chiral symmetry to protect the fermion masses. In the case of gauge bosons, you had gauge symmetry. But here, what supersymmetry does is really to introduce an additional symmetry that links the boson to fermions, and which makes that for each particles you have a partner of different spin, difference of which is difference of 1/2. So and this basically gives you an additional doubling. It's really doubling the spectrum, and in fact a little bit more because you need 2 Higgs doublet, but in fact it's doubling the spectrum. And this spectrum, first of all, will make that first of all, the corrections to the Higgs mass that are made by any particles and which generate these quadratic divergences are cancelled by the corresponding supersymmetric particles. So there is no more quadratic divergences. The divergences are logarithmic. In fact, there are 0 in case of exact supersymmetry and only logarithmic in this if the supersymmetry is broken at the scale of, say, at the scale. So it's only, and a logarithmic contribution, you can just allow it. And second, and this is a very important aspect, is that these new particles also contribute in the running of the gauge couplings. And in fact, and this is one of the magic points of MSSM, of the minimal supersymmetric extension of the standard model, even in the minimal option, you can make that such a spectrum makes exactly the missing contribution, which allows for the 3 gauge couplings to converge and meet at a single point at the scale of 10 to the grand unification scale, 10 to 16 GeV. For me, that was really the argument which made that supersymmetry, that pushed me to study supersymmetry in detail, of course. Okay, and on top of that, you had another argument, which was also one of the driving force behind the supersymmetry. It had, in fact, the best candidate for dark matter, because the lightest supersymmetric particle, if you have a discrete symmetry imposed on the various couplings of the new particles, that allow you to get rid of many problems of physiological issues of the model. If you allow for this discrete symmetry, which goes parity to be exact, to be conserved, then you have the lightest supersymmetric particle is stable. And it has exactly the right properties, the mass range, the couplings, in order to have the desired cosmological Rayleigh density. Okay, so these 3 arguments, the fact that it kills all the lambda squared terms, it makes unification of the gauge couplings, it allows for dark matter explanation, are really the driving. I mean, make that this theory is supposed to be the best one that you have in town. Okay, of course you can also explain naturally the Electroweak symmetry breaking. The idea is that in fact the mu square that you have term that you had in this scalar potential of the standard model was really positive at a very high scale, at the ground unification scale, but there is a normalization group evolution of this mu square term, which makes that at Electroweak scale it becomes negative. So you have really a perfect explanation of the symmetry breaking in the Electroweak sector of the standard model. I mean, in terms of some supersymmetry breaking. Okay. There are also other ingredients, more formal. Of course, it includes gravity. If you really want to insist, it is part of supersymmetry. Well, there are other arguments which make that supersymmetry became really a must. Okay. Now, the problem is that, of course, LHC searched for supersymmetric particles, and the answer is really depressing, because the strongly interacting particles now are are forced to be heavier than 2-3 TeV. This is the case for quarks and gluinos. The Electroweak scale, the Electroweak particles like leptons and charginos and neutrinos, the superpartners of the gauge bosons and the Higgs bosons, are expected to be at the few hundred GeV scale, and therefore you are again in this case losing the naturality of the model, which tells you that everything should happen at a few hundred GeV scale. Now that you push the scale to a few TeV, few TeV in the case of the strongly interacting particles, and a few hundred GeV in the case of the weakly interacting particles, make the theory is less appealing. But it's not yet. Can have. I mean, the theory is indeed fine-tuned, and the fine-tuning now is becoming at the level of 1 per mil, yeah? But at least, if you have the choice between a fine-tuning of 1 per mil and fine-tuning 10 to the minus 18, you don't have to hesitate, of course. But people lost a little bit momentum because at some point we start a little bit to be kind of nervous because these particles turn out to be heavier. But we need to go further and really to check that if they're not there, we really need to push the scale as high as possible in order to make sure that really this naturalness is becoming annoying. Yeah, but for the moment, despite of many people are starting to worry, I think that the fine tuning of 1 per mil is still acceptable. Okay, it's a psychological problem, but it's still acceptable. Let's now please go to the last slide, I think. So, sorry for being maybe basic, yeah, but I think that we have to keep in mind that there are still, even if we just we have been disappointed, we have been kind of hit by the fact that the LHC didn't discover anything, yeah, apart for the Higgs. We have still to continue because the arguments for beyond the standard model physics are there and they are unchanged. The only change is that the scale at which they are supposed to appear is not the scale of few hundred GeV that we are expecting in the beginning, but it should be a little bit higher, so maybe few TeV, okay? Few TeV, not exactly, but because for the Electroweak, for the weakly attracting extensions like supersymmetry, you have still the possibility of people are still discussing about a few hundred GeVs lepton and Neutrinos in the context of the G-2. So these are not big numbers. A few hundred GeV is still the Electroweak scale. After all, it's not far from 250 GeV. So there is still the possibility of having these particles around us. And therefore, you can still produce them in the next, when you turn the high luminosity LHC option or the next REN3, although maybe unlikely because we didn't see any strict, clear signal of something that is close to 3 sigma. Although with all the 3 sigmas that you have around, because I see, for instance, that CMS has at least 5-6 places in which there is a 3 sigma deviation from the standard model expectation. So there is still a chance that something new might happen. So we need to keep still in mind that there is a possibility of having new physics, and this 3 types of new physics. Of course, I didn't discuss the other option, which is the agnostic option of saying, okay, after all, we have to go ahead because everything can happen between, say, 10 TeV and 100 TeV, and 1% precision, 10% precision and 1 per mil precision. So everything can happen, and therefore any type of beyond the standard model physics should be considered. In particular, now if we look at what happens in B physics, all these B anomalies hanging around, there are 4 or 5 of them that are hanging around. The models that have been invoked, in fact, in order to fix this new physics are not all these 3 that I'm discussing. People are discussing Z primes, they are discussing leptoquarks, they are discussing plenty of other things that are nothing. So you have also to check the fact, to consider the possibility of having other stuff hanging around. So it's clear that you have to keep going on and to keep to search for new physics. Okay. Now you have to do it through 2 ways, and these are the usual ways that we are discussing. Entirely this week, yeah, you have to make more precise measurement of the Higgs properties, to make that everything is measured at the level where you can really probe this high scale. And of course, and this has been discussed less, but it's a very important aspect, and this is the question that has been asked to the previous speaker, how far you can go in the mass scale for supersymmetric particles in the 100 TeV collider. This is a very important question. It's clear that now it's 1 TeV for the Electroweak states, but it could be 10 TeV in the case of 100 TeV collider, and this gives you an order of magnitude range that you can probe. So you really have to continue and doing direct searches for these particles at not only, of course, at high energies, but also at high luminosities. So last slide, and sorry for the delay of, been a bit late, yeah? So we have really to continue, And this is my last. I like to, I like always to say this because discovering the Higgs was not the end. It's not even the beginning of the end. It's really, for me, it's, well, first it was clear that it was the beginning of the campaign for the precision measurements, but I hope it's the beginning also of the discovery of something beyond it. Okay, and as I said, it might be that it is something that is related to the three avenues I discussed for new physics. You find supersymmetric particles, some Kaluza-Klein excitations, or some technical fermions, but you never know. Maybe we can find something that is completely different from all what we are expecting, and this will be even more interesting issue. Okay, interesting situation. So please keep going, and we will know if there is no physics or not only at the end of the battle. Okay, so please go ahead. Thank you very much, and sorry for the delay.
Thank you.
Thank you for such a nice talk. It was a very different way of giving the perspective of Higgs within the standard model and then beyond the standard model. Thanks a lot, Professor. And I think now the talk is open for few questions. So let me see if there are any raised hands.
Everybody is spellbound. No, it was really a very nice talk. Good that you didn't have too much interference with your PC.
So I had one small question on slide number 5 or 6 where you talking about gravity.
Yeah.
Can you go to slide number 5 or 6?
Number 5, you say? Okay, sorry, but I. Okay.
Okay, I'll go to slide number 5.
Yeah.
Okay.
So maybe this is just my misunderstanding. The way I understood that if you have the quantum gravity and the quantum of the field is a spin to particle, but I was a little bit intrigued by your statement, graviton of spin to complicated. I mean,
this is subjective. Yeah. For me, at least, it's very complicated. Yeah.
I see. I mean, are we saying that there is something else like alternatives, like where you have the?
No, not at all. Not at all. What I'm saying is that contrary to spin one particles, where you can really do the quantum, the quantization, where you can everything is well defined, etc. In the case of a spin 2, there's a problem. I mean, you cannot really make a kind of coherent quantum field theory for gravity. This is my only my goal.
Now it is clear. I mean, I'm sorry. I was thinking that, okay. I get it now. What you want.
I'm saying is that you don't have any QFT for the moment, and it's not this quantum gravity is not the level of QED, basically.
I mean, we don't saw the classical gravitational field, so then we have to see the quantum.
Yeah.
And
as I said, one of the pillars, in fact, I said it's 3 pillars that on which the standard model is based. The first one is it's a QFT. Yeah, it's really special relativity, where you need only special relativity and quantum mechanics, and therefore, if you have to include the gravity in the games, you at least have to. Special relativity is there, but the quantum aspect is not. Okay.
Right. The last question I had is more towards our end, like when you talked about this kind of top to bottom approach for, let's say, be it supersymmetry, be it extra dimension.
Yeah.
I was thinking, like, given the state the field is in, isn't it we should be more talking about bottom to top approach, more like a data driven, like what people are talking of effective field theory or something like, because I don't know, like top to convincing the funding agency that build FCC, HH, where we don't have any kind of clear cut thing that what the new scale of the new physics should be. Maybe is it fair to say we should more look at the bottom to top approach, like more data driven approach?
No, I agree with you that this is our main problem. Yeah? For the Higgs, for the Higgs, we had really a boundary. We had the fact that we knew that something should happen at 1 TeV because we had very strong argument, which was unitarity. Okay, we need unitarity and also high precision measurements because all the fit of the Electroweak observables was telling us that there must be an object of 100 GeV. In fact, there was in the context of the standard model, there was a bound of the Higgs mass of something like 160 GeV or so. So in the case of LHC, okay, we had the unitarity argument at least, which was telling us that something should happen at 1 TeV, and unitarity is something very strong. Now, it's true that all the arguments that I was really putting forward are coming from naturality, and naturality is less solid and less firmly with the firm basis as compared to unitarity. But well, this is all what we have in store. Yeah, sorry. Yeah, yeah. So it's clear that we have to be fair and we have to tell these guys that we are not sure. But we have all the means that we have now favor this option, but of course we cannot guarantee it because we can, as I said, we can still have. First, the hierarchy problem might be just ignored. First of all, okay, and second, and if it's the case, I was alluding about this possibility of unifying and explaining everything in the context of SO10 with an intermediate scale at 10 to the 11 GeV, 10 to the 12 GeV, okay, which is basically untestable, okay. So it might be true that, but until we tried, we can never be sure. So let's keep going and do the thing. And one of the arguments, in fact, that we should put forward is that if you don't try, you don't get, and that's it. And we have to be fair. This is exactly the only thing that is left to us to do. We have to go forward, maybe continue with our 3 avenues as benchmarks, yeah. But we clearly have to say that we cannot be 100% sure, but we have arguments which tell us that things might happen at the level at scales or at places which we can probe at the high luminosity LHC in a few years, but also in 20 years or 30 years or whatever at higher energies or with higher luminosities or with other machines. So I mean, it's clear we don't have the choice. That's the point. Yeah.
Thank you.
Okay. I just have one question. So, I mean, the recent measurement of the W mass by the CDF, I mean, does it inspire any of the new scenarios, or it can be kind of accommodated within the?
Yeah. Alors, I didn't want to, because I alluded to the G-minus 2, but I tried to avoid the discussion with the MW. Bon, first of all, the problem with the W mass measurement is that not only it conflicts with the standard model expectation, but also it conflicts with all the other measurements that have been done on MW. If I mean, the 5 sigma difference with they claim 7 sigma, but apparently now there are a few things that maybe that have to be adjusted. For instance, you have to put more precise discussion of the backgrounds. You have to take into account the W width. You have to take into account more elaborated set of PDFs, etc. If you do this properly, apparently the discrepancy is not anymore 7 sigma. It's something like 5 or even less. Okay, but in any case, not only there is a more than 5 sigma discrepancy with the standard model expectation, but there is also 5 sigma discrepancy with the other measurements. So it's only when you average things that are completely widely different that at the end of the day you get a 5 sigma difference between the expectation and the average. So a first problem that has to be explained in the very beginning is why this measurement is completely different from the others. So for instance, we now I don't know whether it's CMS. I think that is. I hope that we will have another measurement of MW, which is as precise as the one of Atlas, to have another view of the situation. But there is already a problem of experimental nature. And second, theoretically, this can be explained. Well, maybe 200 papers which appeared in the literature to explain this. And of course, you can explain it with basically all the options that you have on the table, yeah? And that for instance, in particular, the ones I discussed, by just making very, very small excursions from what people did in the past. For instance, you can just decide that you have indeed a minimal supersymmetric standard model with the additional Higgs particles, and you have just to manage in such a way that the mass splitting between the Higgses is not zero or small, but it's big enough in order. So there are many ways, in fact, to play in MW. But of course, you are right. You need to have some physics that is at the scale that is probably possible to probe within the next decade. So that could be an argument in favor of continuing the campaign of precision measurements and dedicated searches, but it's really, you have to keep in mind that we have first to solve the problems of why this measurement is different from what has been measured by the other experiment. In particular, lab measurements are maybe less precise, but they are more safe because, as Jenny List was discussing in her talk, E+C-minus collisions is a very safe place where plenty of uncertainties are disappearing. So any measurement is trustable, yeah. So we have to. I would be happy. I even wrote a paper about it. I would be happy if this appears to be true, but I would like first that some experimental issues are resolved before.
Okay. Yeah, I think that's well said. Thanks a lot. So I think we can close the session. I thank all the speakers. Yeah, I'll hand it over Kajuri.
Oh,
So
okay.
let me first thank all the speakers for giving excellent talks. And now I hand it over to Kajuri.